Good morning, everybody. I am live now. Sorry it took me a minute to get back to live. Not get back to live. Sorry it took me a minute to get live. It Things weren't loading right for a second, so it took me a minute to get everything set up. While people gather, I'm going to get my paint set open. Get my pen ready. Good morning, Jacob. All right. I probably would have rather done these in a different order because I don't know. Current is pretty simple in a parallel circuit. Uh, and yeah, let's go ahead and get into it. Branch circuits in a parallel circuit are always greater than total current. That is false. So in a parallel circuit, the currents add together. So to go to Kirchhoff's current law, let's see. There we go. Where's my mark? There we go. Okay, Kirchhoff's current law states that uh, current in, so into a spot on a circuit has to equal I out. So if there's a break in that circuit, so if you have a full on parallel circuit, if you have a full on parallel circuit and you have 5 amps going here, then and you work it out. So let's say you have 120 volts and 80 ohms. Yeah, this can still work. I was like, oh shit, give myself numbers that don't work. 120 volts, 80 ohms. Well, we can use Ohm's law. So 120 divided by 80, 1.5. So we know there's 1.5 amps traveling through here. What is the current? We have all the information we need to solve the rest of the circuit. And so in a parallel circuit, let's go through all of the units right now. So R, I, E, and P. Well, remember in a series circuit, current stayed the same and voltage adds up. In parallel, they swap. Voltage is the same at all points, or on all parallel legs. So this leg has 120 volts, and this leg has 120 volts. A good example of parallel circuits that you're used to reacting with or dealing with is all the receptacles in your house are parallel with each other. Excuse me. Current is going to add up. So if we have 1.5 amps, 5 amps total, 1.5 amps here, well, I know that this one is going to be 3.5 amps, right? Yes. Because any current that didn't go this way has to go this way. You see what I'm saying? And whenever you get past here, you have 5 amps again because it's all come back together. Resistance is the most complex part of a parallel circuit. So there's 3 or 4 different ways to do resistance, but just know that the total resistance is always lower than the individual resistance values because it's possible for current to go other directions and it's not forced to go through the one resistor. It would be like if you're at a checkout, you're waiting to check out at like HEB, and Ethel is at one checkout line and she's checking out one person per hour, and you have some young woman or young person checking out people at another checkout line. She's doing like 4 people an hour. Well, it's easier for them to get through even if you added another person that's only checking out 1 person an hour. So you have somebody checking out 4 people an hour and somebody checking out 1 person an hour. This would be representative current. So you're getting 5 people an hour. Even if you added another checkout line that's only checking out 1 person every 2 hours, so half a person an hour, you're still getting 5.5 people out of the store per hour, which is an unreasonably low number. But like I would just leave my stuff in the cart. But you get what I'm after. The more lanes you have in parallel, the lower your resistance to getting out of the store is. So the formula that I would like you to remember, there's 3 or 4 formulas in the code book, in your DC theory book, about how to calculate resistance in parallel. They're all basically the same formula, just at different states of being. The one that I would like you to remember is R total is equal to 1 over 1 over R1 plus 1 over R2. It's called the reciprocal formula. Whenever we get to the resistance lesson, I will go over all of them, but here is the jack of all trades one. The others have a very specific use case. Like some of them can only be used with 1 or with 2 resistors. Some of them can only be used if all the resistors are identical. This one you can just keep adding plus 1 over R3, 1 over R4 dot dot dot, because you can just keep going. You could do 3,000 resistors with this formula. That'd be really difficult, but you can do it. Something like that. Alright, that's question 1. Only took 10 minutes. Adding parallel loads to a circuit will increase the total, so this is false. Already covered this. It will decrease the total circuit resistance and increase the total current. Alright, 2 6-volt sources are connected to supply a 24 ohm load. How much current will flow in the circuit? So, voltage in parallel. Let's select. We won't need this right now. So voltage in parallel stays the same. Uh, let's erase that. So if you had 6 volts and then you added another battery in parallel, well, parallel batteries do not add their voltages, they add their capacities. So 6 volts and 6 volts, your RE total for this is going to be 6 volts. And I think it said 24 ohms. 6 divided by 24, 0.25. So, oh, and power in parallel adds up. So all the different individual powers always add up. So your current is 0.25 amps. The multiple voltages in parallel didn't matter as far as calculating everything. What you're getting out of adding another battery in parallel is runtime. So this circuit will be able to run for twice as long with 2 batteries in parallel. Battery's runtime is measured in amp hours. So if this was a 1.5 amp hour and this was a 1.5 amp hour, well then you have 3 amp hours total. Now, if you put batteries in series, like we were talking about last week, they add up. 0.25. Looks like a lot of y'all got it. Good job. Alright. So, how much current would each source supply to the load? Each one's going to supply half the current. That's why they run for twice as long. So it's going to be half of 1.25, which is, or half of 0.25, which is 1.25. A lot of people got. If a circuit has 3 branches with parallel currents of 10 amps, 5 amps, and 12.5 amps, what would be the total circuit current? So let's So we have a circuit. Oh, I should have just copy pasted. Okay, live and learn. 10, 5, and 12.5. So we have 10 amps, 5 amps, and 12.5 amps. They want to know if we put a ammeter right here, what's it going to read? Well, amperage in parallel adds up, so we got 15, so this is going to be 27.5 amps. So 10 and 5 is 15, 15 and 12.5 is 27.5. Alright, so let's, oh, that didn't zoom in at all. This is, I saw a question that looks like 98 volts to me. Well, find the total current in the circuit by calculating individual branch currents, and then using the sum rule for parallel circuit current to determine the total current. Ah, okay. Oop. Select. Alright, close enough. Alright, so we got 98 volts, 28 and 70. Was it 70 or 7? 70. So, let's do our chart. Our total R1, R2. 28 ohms and 70 ohms. I total, I1, I2. Don't know any of those. The total is 98. And since it's a parallel circuit, voltages stay the same. So E1 is 98 volts and E2 98 volts. Now remember what we said last class. If there's two things in a row, you can solve for the rest of the row. So 98 divided by 70 gets us 1.4 amps. 98 divided by 28 gives us 3.5 amps. So that gives us 9, 3, 4. Looks like 4.9 amps. Let's see how we did. 4.9 amps looks to be the... Oh, my pen's too close to the... looks to be the answer. The next question is, what is the total resistance in this circuit? Well, you could use one of the formulas to find total resistance, or you can just 98 divided by 4.9. Because we haven't gotten to that actual, so 20 ohms. You can see how the total resistance is lower than either of the individual resistances. Alright, so that concludes this lesson. I will be going live at 10:45 with the coverage of the resistance lesson. Let's start the launch. Let's launch the second quiz. See, everything's been taking forever this morning. I don't know what's up. Maybe it's me. Let's see, instant feedback. Alright. And just so you can look these things up yourself, if you go to your blended learning, there is a so DC Theory textbook chapter 5, and then also there's a courseware, Understanding Resistance in Parallel Circuits. Oh, it's very short. I would ignore this. Well, yeah, your book will cover everything in pretty good detail. You can read this. I haven't read it yet, but it seems too short to have any great info. Alright, I will see you guys at 10:45.